And then to understand these Schwarzschild black holes, I will introduce what are known as the critical coordinates. And then hopefully, if time permits, I will just give you a brief discussion about black hole thermodynamics, and then we may talk about some geometric objects which are called as wormholes, and then there are some recent work in this area which are known as the traversable wormholes. So all these things I plan to explain. So before I explain, I should talk about the references. So more or less everything that I talk here can actually be found in this excellent book by Hartle. It's an introduction to general relativity, and Hartle is a very well-known physicist who have done many seminal work in general relativity. So, and he has also written an excellent book on introduction to general relativity, which anybody can actually read and understand. Okay, so most of the material is actually taken from this book, and there is a very popular article on wormholes. Towards the end of the talk, I will discuss wormholes, and most of these materials are borrowed from this article by Morris and Thor. It's a very well-readable article. So there are some results which I will talk, which are technical. So I am not giving you reference to any technical papers. So these are all very general kind of references which anybody can actually read and follow. And I will also use what are called as the Penrose diagrams, and this web page actually explains how to how to make Penrose diagrams in LaTeX, but they give some examples which were good enough for me, so I directly borrowed a number of their examples, although I have also used the help of those examples to draw a few more Penrose diagrams, but most of the Penrose diagrams that I use are borrowed from this web page. So let me talk about something which all of you are familiar with. So metric is a quantity which you can use to measure distances, area, volume, and things like that. And so in a space, if you consider any two arbitrary points which are infinitesimally close to each other, and if you know the separation between these 2 points, and that is for all the points in this space, then you can compute any geometric quantity like length of a curve, or area of a surface, or volume of a region, things like that. So to compute these geometric objects, what you need is a metric. And in our conventional sense, this is the metric that everybody uses in three-dimensional Euclidean space. You consider any 2 points which are infinitesimally close to each other, then the square of the distance between these points is given by dx square plus dy square plus dz square. That is in Cartesian coordinate system. The same distance can actually be expressible in what I called as the spherical polar coordinates. I hope you are familiar with spherical polar coordinates, but if not, then just like here, you consider any point here, you can actually parameterize it by specify it by x, y, and z coordinates. Similarly, you can use the spherical polar coordinates where r is, you choose a origin, and then the distance from this origin is r, and theta is just the angle that the line makes with respect to the z-axis, and phi is the azimuthal angle. Theta is called as the polar angle. Phi is obtained by just taking the projection of the point onto xy plane, and then what is the angle that point makes with respect to the x-axis. So that is my phi. So in terms of these coordinates, the metric is given by this. Now, so this is the standard metric in three-dimensional Euclidean space. But now what I will do, I will impose a constraint by saying that I am keeping this coordinate r to be fixed. So you consider the set of all points with a fixed distance from the origin, you will obtain the surface of a sphere. So in this metric, if you put the constraint r equal to constant, some constant capital R, then this is what is the metric that you obtain, because dr is equal to 0. R is constant, dr equal to 0. So the metric ds square, by the way, this metric is also known as the line element. So the line element basically becomes ds square is equal to r square times d omega 2 square, where this d omega 2 is basically the standard metric on a round sphere. So this is just d theta square plus sine square theta d phi square. Alright? So this is what so this is what, don't worry, I think I will just, and what is interesting about this quantity is that unlike the three-dimensional Euclidean space, the space that you obtain by setting r equal to constant is no longer a flat space. It is what is called as a curved space, and then it is also known as a non-Euclidean space, and the surface of a sphere is one of the simplest example of a non-Euclidean space. And I will give you a brief introduction about what a non-Euclidean space is. So basically, in Euclidean space, you have some standard rules, like you consider the ratio of circumference of a circle to its diameter, you get 2 pi, or for example, the sum of the interior angles is just pi. On the other hand, if you are not in a flat space, then these results no longer holds, and these are the standard results for the surface of a sphere. I will not derive that, but I will explain what is the meaning of these quantities here. In flat space, everybody know what a straight line is. It's just a line which doesn't bend or anything. It is just a straight. Now suppose you want to consider the surface of the sphere, and there is nothing straight here because it's all curved. So what is the analogous of a straight line? So you can generalize it by saying that in flat space, in ordinary space, Newton's law says that if you do not apply any force on any particle, then it is either at rest or it travels in a straight line. Okay? So you just write down the equation of motion for a free particle, and then you solve it. The solution is just a straight line in your flat Euclidean space. You do exactly the same thing on the surface of a sphere. Okay? You just consider the motion of a free particle on the surface of a sphere, and so therefore you again write down the equation of motion, the standard Newton's laws you can write. The force is equal to 0, so the acceleration is equal to 0. But now you impose this restriction, r equal to constant. The radial coordinate you set it to constant. Then the equations, you will get a set of equations, and then you can solve them. And then this will be the analogous to the straight lines. Okay, so these are what are called as the geodesics in the curved space. The analogous to straight lines are basically geodesics. So they are obtained by solving the equation of motion of a free particle in that particular space. And in the case of a circle, it's very straightforward to obtain. Anybody can work it out. And these are all the great circles on the surface of a sphere. Okay? So then you can consider, for example, a triangle basically is just intersection of three great circles here, so that will form a triangle. And similarly, a circle on the surface of a sphere you can form by considering an origin, and then you consider the set of all points which are at a fixed distance from from the origin. Okay, so that is a circle. So then the radius of the circle will be the distance of the distance from the origin. Okay, that's the distance on the surface of the sphere. Remember, there is nothing other than the surface of sphere. I mean, usually you can think a sphere to be embedded in three-dimensional space and all those things, but here we talk only of these points here on the surface of sphere, only the points which satisfies this constraint uh, r equal to r. So there is nothing inside the sphere. Okay, it's all the points on the surface, and therefore the distance is just length of this curve here. That the radius is just this. Okay, and then you can simply see that the ratio of the circumference to diameter is just given by this interesting formula. It's straightforward to derive this. Something which is a little bit less straightforward is the interior angle sum. Okay, it is given by this. In fact, if you look at Wikipedia, there is a whole there is a big article on trigonometry on the surface of a sphere, and anybody can just for fun you can spend a couple of hours and then derive all that. There are many interesting formulae there which you can go through. The point is that the conventional axioms of Euclid that we are all familiar with no longer hold on the surface of a curved space. Okay, so when you say a space to be curved, there is a systematic way to define a curved space. Basically, what you do is that you can consider a closed path, and then you can what is called as parallel transport. You take an arbitrary vector and then you transport along a closed curve in such a way that if you consider any two infinitesimal points which are close to each other, then this vector is parallel. Okay, so that way you transport it along a closed curve. If this vector comes back to itself for any arbitrary closed curve, then this space is a flat space. If it doesn't come back to itself, then this space is curved. So that is how you define how it differs when you turn it around a closed curve is determined by what is called as the curvature of this curved space. Okay, so this is basically about curved space. Now what we will do is that we will talk about space-time. Okay, so generally we live in 3 plus 1 dimensional space-time, and all of you know in space and time are not exactly different from each other. Basically, what is space and what is time depends on the inertial observer. If you are one inertial observer, another person moves with respect to you in a uniform velocity, then of course the notion of space and time are mixed. Okay, so they are not separate from each other. So in that sense, you have to treat space and time on an equal footing. And if you talk about the metric, then in relativistic theories, you have to talk about the metric of the 3 plus 1 dimensional space-time, because space itself doesn't have an invariant meaning if you just separate it from time. And here, this is what is the metric of 3 plus 1 dimensional space-time. This has an invariant meaning. If you consider 2 points which are infinitesimally close to each other, in this 3 plus 1 dimensional space-time, then this quantity doesn't have an invariant meaning. Okay, it depends on what inertial observer that you choose. On the other hand, this quantity here with this minus c square dt square is actually independent of the inertial observer. Okay, you consider any inertial observer, this is just invariant. And also this gives you a notion of what is time and what is space, because see this, you consider in some books this a point in space-time is also called as event, okay? So it's just a point in three-dimensional space at a given time, okay? If time changes, then this point also changes, okay? So in that sense, you have a point in space-time, and because it's four-dimensional space, there are four coordinates needed to parameterize this point. I will call the coordinate to be a time coordinate, provided you keep the other three coordinates fixed and then vary this particular coordinate, then ds square should be negative, okay? If that is the case, then you call that particular coordinate to be a time coordinate. On the other hand, if you fix three coordinates and then vary a coordinate, if this quantity is positive, then you call that to be a space coordinate. So there is no invariant meaning of time. You can redefine your time, but every time you redefine your time, it should actually follow the same rule. Alright, so that is what, so therefore, you consider two events in space-time, so basically 2 points, you call them to be time-like separated if this quantity is less than 0, in the sense that a particle can actually travel from one point in this space-time to another point in space-time if these two events are time-like with respect to each other. The events are said to be light-like with respect to each other if this quantity is 0. Okay, so you can send a light signal from one point in this space-time to another point in space-time, and then the points are basically space-like if this quantity is positive. Okay, so this is what I mean. And then there is a very interesting notion. It's basically called as a light cone. Okay, so light cone is used in basically to to consider various trajectory of particles and then see whether they are light-like or space-like or time-like, and then how a particle can actually so I'm using a term which is called as the world line. So world line basically is a trajectory of a particle in space-time. Okay. So suppose in 3+1 dimension you consider the motion of a particle, and then you want to know how this particle moves. Then there is this concept of light cone. It's used basically to discuss the motion of a particle in this 3+1 dimensional space-time. Basically what happens if you consider the propagation of light, here I am just considering it for 1+1 dimensional space-time. So I am drawing along the y-axis time, c times actually time, and along the x-axis it's just the x coordinate. So suppose you just send from the origin, you send a light signal, okay? It can either go to left or it can go to right. So this is what the light signal will trace in this graph, okay? Because remember this is CT and this is X, okay? So it will take, of course, the time this much. I mean, when you want it go to unit length, it will take this much interval of time. Okay, so therefore you get a straight line at a 45-degree angle this way. Now, if you consider the propagation of a light in a plane, then instead of two straight lines, it will trace a cone. Okay, in that sense, it is called as light cone. And if you consider the propagation of light in 3+1 dimensional space-time, then instead of a circle, you get a sphere. Okay, so basically here, if you just consider a constant time section, you get 2 points. If you consider the propagation in 2+1 dimension, you get a circle, a constant time section. In 3+1 dimension, you get spheres. Okay, So the cross sections are basically spheres. Now, if you consider the propagation of a particle, so this is just basically the world line of a particle. Okay, a particle can travel like this. So what is important to remember is that you consider the slope of this trajectory, this is the world line, at any given time. If you want to compute its slope, it should always be greater than 1. Okay, because the velocity of a particle must always be less than that of the velocity of light. Okay, if it is a massive particle, it travels at a speed which is less than the speed of light. So therefore, it should always be the slope should always be greater than 1. If it is not, then no signal can actually connect between these 2 points. So in that sense, you consider any point in this space-like region that is not connected. You cannot send any signal to any point here in this region from origin. Okay, but you can consider any point here in the time-like region. You can send a signal by a particle which is traveling to that point or so. Okay. On the other hand, light signals only travel along these directions. So that is how the light-like paths basically travel along these directions, whereas the world line by any particle actually travels this way. And also there is this, when one discusses basically the causal structure of space-time, okay, which basically means propagation of various particles, world lines of physical objects, how light travels, and so on and so forth, then you should also know about the behavior at large distances and at large time, and so on and so forth. So there are various kinds of infinities which are associated, okay, and these are what are called as future time-like infinity, which basically means you can take the limit t goes to infinity, okay, whereas r can be any point. Okay, it need not be spatial infinity. It is just t goes to plus infinity. Similarly, if t is minus infinity, then it is past time like infinity. These are denoted by I plus and I minus. Similarly, future light like infinity basically are the points in this space-time diagram where light signal can go. Okay, so these are basically light like infinity. They are denoted by this symbol here, which is known as scry. So scry plus is the future light like infinity. Similarly, scry minus is past light like infinity. It is obtained by taking x plus ct goes to plus infinity. Okay, whereas this one is obtained by taking x plus ct equal to minus infinity. So these are for right moving signals. The minus sign is for left moving signals. Similarly, space like infinity is basically denoted by I0. Okay, so I'm drawing the same diagram here, and only thing is that here I am indicating all the infinities here. Okay, so this light signal is time goes to infinity. A light signal can go to scry plus. It can also go to scry plus here. On the other hand, if you take simply t equals to infinity, the world line of a particle will go to I plus. Okay, a particle, not light, some massive particle, as t equals to infinity, it can go to I plus. Similarly, the particle comes as t goes to minus infinity, far past the part it lives in I plus, whereas light signals come here. Okay, and this is the world line of a particle, and as you can see, the slope here is always lying at any point you consider. The trajectory always lies within the light cone at that point. So this is how the space-time diagram looks like. There are something which are called as the Penrose diagrams. So what these Penrose diagrams do is, you map the whole space-time diagram into a finite region of space. Okay, and how do you do that? You just reintroduce, you redefine instead of x and t. I am using the coordinates u and v. Okay, and so I am just making a change of variables. But now you see, you have u and v takes finite the values in finite region. Okay, and what is interesting about this map is that the entire thing is mapped into finite region of space-time, and the structure of the light cone remains the same, in the sense light rays still travel at 45-degree angles. Okay, and so that is the advantage of this. So various infinities that I have described in the previous slide basically turns into this. So if you take x plus or minus ct to infinity, then that corresponds to u plus or minus v to plus pi by 2. Similarly, if you take this to be minus infinity, this corresponds to u plus or minus v to be minus pi by 2. And similarly, I plus is basically goes to t goes to infinity. T goes to infinity corresponds to u equal to 0, v equal to pi by 2, and so on and so forth. Okay. So therefore, the picture that I had here is mapped to this compact region here. It's the same picture. This transformation that I have made in the previous slide, this is what is called as this is just a word, it's called as the conformal compactification of Minkowski space. It basically takes the whole infinite region and maps it to finite region. So what this transformation does is, this transformation preserves the angles. It doesn't preserve the length, okay? It preserves the angles. So therefore, the structure of light cones, etc. still are the same. And here, as you can see, you have a particle which at t goes to minus infinity. It is at past infinity. It is I minus. It starts from here. It goes wherever it wants, and then finally, as t goes to plus infinity, it goes to this point. So this is the word line of a particle. On the other hand, light rays. So the advantage of this transformation is that light rays always, even in this new coordinate system, the trajectory of light rays are basically straight lines which make 45-degree angle with respect to your x-axis. Okay, so light rays still go along this direction. Now you see, because light rays can go to anywhere. Okay, as t goes to infinity, a light ray which starts from here can go to this place. Okay, so this chi plus is made to this entire region. Similarly, a light ray at infinity, past infinity, a light ray can come anywhere from here. Okay, so chi minus is made into these two regions. On the other hand, the spatial infinity is made to this point and this point here. So these are, so this is what is called as Penrose diagram, and so this is what it is, just in 1 plus 1 dimension, Penrose diagram in 1 plus 1 dimension. If you consider 3 plus 1 dimension, the Penrose diagram is mapped in this RT plane. Okay, now instead of x and y, you make this transformation with r and t. In place of x, you make r, but now you see r can only be positive. Okay, so instead of plus and minus sign, you just consider the minus sign, and that will give you this diagram. So what is the point here is that you consider any point. I am suppressing the angular coordinates here. So any point, there is a sphere sitting here whose radius is basically determined by the value of this radial coordinate at that point. Okay, so by suppressing the angular coordinates, I am plotting the Penrose diagram of this 3 plus 1 dimensional Minkowski space here. Now it's only the half of the region because R can only take positive values. Okay, so this is how it looks. Now what we will do, so this is basically what is called as the flat space-time. This is the geometry of flat space-time, and in terms of diagrams, this is how it is made. But now what we will go to the geometry of a curved space-time. Einstein's general relativity says that if you place matter in space-time, then it modifies the geometry. It makes the space-time to be curved. Okay, so the simplest example of a curved space-time is what is called as the Schwarzschild space-time. Okay, it's basically the geometry of the space-time outside a spherical object. Okay, you consider a mass M with a spherical symmetry. Okay, you consider a star which is not rotating or something. It's just static. It's just lying there. No, you don't even assume static. Okay, just consider an object which is spherically symmetric. Okay, so if you have a spherically symmetric matter, then outside this spherically symmetric matter, the geometry of the space-time will look like this, and this is what is called as the Schwarzschild geometry. Okay, so the metric that we had earlier, remember the flat space metric is without this factor here. It's just minus c square dt square plus dr square plus r square d omega square. Now if you put a spherically symmetric matter, then the metric outside that matter, okay, actually is modified, and this is how it is modified. Okay, and here this Rs is just a parameter. It is given by the mass of this spherically symmetric object, and then g is the Newton's constant and c is the velocity of light. Okay, so I will use this parameter Rs all the time. So this is how it is. This is the geometry. How will you know this geometry is correct? You just consider the trajectory of a particle outside a spherically symmetric body. Okay, what is the path it follows? You consider it's a free particle which is moving in the influence of the gravity, or light propagates outside a star. Okay, so you consider distant lights which come near sun. What is the trajectory they follow? Okay, and you can derive using this geometry what is the trajectory that they should follow, and it indeed turns out that this is correct. This is the correct geometry, and this is what is a unique solution to Einstein's equation. Okay, so this is what is called as the Einstein's equation. So basically this is the equation which determines the geometry of the space-time. Okay, if you have a matter instead of 0, you have something like 8 pi g divided by c fourth times something which is called as the energy momentum tensor of the matter. Forget about all these things, but this is just the analogous to the equations of motion. Okay, you in general relativity, this metric is a dynamical quantity, and probably if I wait, I shouldn't actually keep it idle for a long time. So this is how the metric looks. Okay, so this is the metric of space-time outside a sphere, and this is experimentally verified. And what I was saying is that this comes, so this geometry comes by solving the equation of motion. In general relativity, the metric itself is the dynamical variable. Okay, and this equation gives you a set of second order partial differential equations involving g mu nu. This g mu nu are basically various components here. Okay, this is where I have written ds square is this. So I am just denoting x0, x1, x2, x3 to be the space-time coordinates. So the coefficients are basically, so this is a 4 by 4 symmetric matrix, and these are the elements of this matrix. Okay, And what happens in general relativity is that these are the dynamical variables, and this is actually a set of how many 10 second order differential partial differential equations. Uh, you can solve them and then you can obtain this solution. It's not as complicated as it looks like. The only assumption that goes here is that the geometry is spherically symmetric. So one can assume spherical symmetry, and then one can write down this equation, one can solve. This solution comes as a unique solution. As a byproduct, it so happens that this solution becomes static. Okay, a static solution is the one where the metric is independent of time. You can see that the metric does not contain the time coordinate, but that's not enough for this to be static. So whenever the metric is independent of time, it's called as a stationary space. For example, you consider something is rotating, the geometry outside a rotating star or something like that. Okay, so that will be stationary. The components of the metric will be still independent of time. A stationary space is called static if it is invariant under t goes to minus t. Okay, if there is a time reversal symmetry in addition to stationary, then it becomes static. Okay, and this is what is the static spherically symmetric solution to Einstein's vacuum equation. Okay, and this is in fact it's a unique solution. The only thing that depends, the solution depends on this mass m here. Okay. Now let us look at some typical numbers. You consider still this geometry. Consider this geometry for our sun. Okay. So for sun, if you compute numerically this quantity Rs, okay, this is roughly of the order of 3 kilometers. On the other hand, the size of sun is something like 7.5 into 10 to the 7 into 10 to the power 5 kilometers. So it's the size is typically very much larger than this number Rs. Okay, but let us assume, just as a mathematical idealization, we will see later that it is in fact possible. But let us assume that you have a body for which this Rs is actually less than the size. Now if you assume, and then you can look at the geometry here, then this geometry becomes a little bit non-trivial. Okay, for a spherically symmetric star like sun or so, this is a perfectly well behaved geometry. But in the special case where the size of this object is smaller than this parameter Rs, this is not so well behaved, because you can see there is this term here with minus 1 to the minus 1 power, and this at some point this quantity becomes infinity. So this actually diverges. So when this happens, you call that to be a singularity. Okay? So the metric is not well defined. It either becomes 0 or it becomes infinity. Okay? Now suppose you consider this solution, and let us assume that this is true all the way up to r equal to 0. Okay, then there is another singularity at r equal to 0 also. Okay, so there are two singularities. One is located at r equal to, I am not going to go through it in detail, but you can consider this metric in flat two-dimensional space, metric on a plane, and then you can make this change of variables, and then you can see that this indeed actually goes to infinity at x tilde equal to 1. But you know that's not actually a singularity, because it's a perfectly well behaved metric. It basically is a bad choice of coordinate. In fact, even if you go to this metric in two-dimensional space, you can write it in polar coordinates, dr square plus r square d theta square. Okay, then at r equal to 0, the theta component of the metric becomes 0. So again, r equal to 0 is a singularity, but there is nothing special about origin. Okay, it's just a point here, nothing funny happens, it's just the bad choice of your coordinate system.
In that sense, this singularity is also a coordinate singularity. It basically says that the RT coordinate actually, which goes from I minus all the way to I plus. Okay. So these are basically space-like surfaces. Okay. On the other hand, these are time-like surfaces. Okay. All right. But now you see, if you take R equal to Rs, although I said there is nothing special happens, there is something very special happens at R equal to Rs, because if R is greater than Rs, you consider some constant R surface, okay? R equal to constant, you get a surface like this. This is a time-like surface. On the other hand, if you take R equal to Rs, you get this line here, okay? This is no longer time-like, this is light-like, okay? This is at 45-degree angle with respect to the x-axis. So this is actually a light-like surface, or this is what is called as a null surface, okay? So this is very different from R equal to constant surface outside, I mean, for R equal to constant, but it is larger than Rs, okay? Then you get a time-like surface. Here, at any given time, you take R equal to constant, you get the surface of a sphere. It's just a time-like surface, okay? So, but this no longer happens. So that's just a point in space-time, because every point corresponds to a sphere. Okay? In the space-time diagram, it is just a time-like line. Okay? These lines are basically these. On the other hand, this is a null line. Okay? This is a light line. Okay? So the horizon is a null surface. Okay? And if you go beyond here, then eventually what happens, the R equal to 0 actually maps to this. Okay, so maps to this line here, that is important. And eventually what happens, whenever you consider the trajectory of any particle, if it is outside the horizon, outside R equal to Rs, the particle can go to I equal to infinity, as it can go to spatial infinity. A light signal can go to Sky plus, but if you are inside the horizon, if R becomes smaller than Rs, eventually it is hit, and then it hits this R equal to 0 singularity. Okay? So this is the geometry, but this is the geometry which is obtained by assuming that it's this geometry of the Schwarzschild. This is the metric that I had shown, that it is valid all the way from R equal to 0 to infinity. Okay? So then this is what is the Penrose diagram for that particular geometry. But in real life, that is not what is happening. What happens when you, so how do these black holes form? By the way, this geometry is called as a black hole because you can see
5 minutes.
for R, inside this region, if you have some object, there is no way it can come out. Okay, not even light. Light can always live on the R equal to Rs surface. Okay, there is one possibility because it's 45-degree angle, so a light can all the way it can go here. Okay, that basically means that it can be stationary at the surface all the time, or it can go and then it can again go 45-degree angle. It will hit R equal to 0 singularity. There is no way for light or any other object to come out of this region. That's the reason this space-time is called as a black hole. Okay, and really in real life, what happens? You consider a star. Okay, then the star actually it can burn, and then it can run out of its fuel, and then it can explode. It can contract, and then it can have a supernova explosion. Again, it can the core is heated up, and then you have the elements which combine to heavier elements, again they radiate. This chain will continue. Eventually, what happens if the star runs completely out of fuel, okay? The elements are heavy like iron or so, then they cannot combine again, they cannot burn and combine into some more stable elements. So eventually it will run out of fuel, so there is not going to be any radiation pressure. By gravity it is going to contract. And there is something which is called as Chandrasekhar's limit, okay? So if the mass of the spherical object is greater than roughly 3 times the mass of sun or something like that, eventually what will happen, the object will contract to a size which is smaller than r equal to rs, its Schwarzschild radius, okay? Then what is going to happen, it is eventually going to contract and it will turn into a black hole. So this is the Penrose diagram of a star turning into a black hole. And as you can see, after r equal to rs, everything actually goes and then hits the singularity. Okay. So I think I should run a little bit fast. So let's talk a little bit about the horizon geometry. So this r equal to rs, not 2m, it's r equal to rs is actually what is called as a null surface. It's a 3-dimensional null surface. If you take the constant time slice, then this is rs square times d omega 2 square. You can compute the area of that quantity, okay? This basically simply becomes 16 pi m square, and this formula we will use a little later, and dm from, by directly differentiating this, you can see that dm is just equal to this, where I have identified kappa to be 1 over 4m, okay? So this is what basically all about the horizon geometry that I wanted to discuss. The solution that I have talked here has spherical symmetry, okay? But in real life you have stars which are basically rotating, they have some angular momentum, and so one can consider rotating solutions. I am not going to write down the solution here, but they are known as the curve solutions. And again, you can obtain black holes from the curve geometry, and then there are 2 horizons instead of 1 horizon, there are 2 horizons. And there is one thing that I wanted to point out here. You see, this is a null surface, anything which is 45 degrees, that is the trajectory of a light ray, so that is a null surface. Anything, you consider a surface which is like this, okay? This is a time-like surface, okay? In the sense, you consider the slope, it is always greater than 1. On the other hand, surfaces like this are space-like surface. So these are all space-like surfaces, whereas these are time-like surfaces. And you can see the singularity, it is actually not a point, r equal to 0 is not a point, but it's a surface, and it's a space-like surface. This r actually becomes like a time coordinate inside the horizon, and r equal to 0 is, the singularity is actually a space-like surface, okay? That is what is happening in Schwarzschild solution. The rotating solution, something very much similar happens, except that there are striking differences. There are 2 horizons here. One is an inner horizon, another is an outer horizon, and the structure of the singularity is also a little bit different. It's a time-like singularity, and it doesn't happen only at r equal to 0. You have to specify the value of theta also. So r equal to 0, and I think theta equal to pi by 2 or whatever. So that is the singularity, okay? And again, you can compute, it's looking at the metric, you can compute the area of the horizon, and one can differentiate, and then one can obtain this formula. It's which is relevant later later. So there are many solutions this way you can obtain. Okay, the Schwarzschild solution that I have discussed. You can also consider, if you assume spherical symmetry, you can put some charge on the black hole. So the Schwarzschild black holes doesn't have any charge; they are completely neutral. But you can mathematically construct electrically charged black holes, which are spherically symmetric. They are called as Reisner-Nordstrom black holes. Okay. Similarly, rotating black holes. This is Kerr black hole. If it is also charged, it's known as Kerr-Neumann black holes. You can. These are electric charges, but you can put magnetic charge also. Mathematically, you can construct these solutions. What is interesting about these black hole solutions is that you saw the Schwarzschild solution. It contains only one parameter, that is m. Okay. So if you give m, the solution is uniquely fixed. Similarly, if you give m, q, j, this solution is uniquely fixed. So there are uniqueness theorems about these black holes. Okay. So one can prove that these solutions with this many charges, you can construct unique solutions. Okay. So that is what is relevant for our later discussion. But there is something very interesting which was raised by Bekenstein some time ago. He said that the existence of black holes will actually violate second law of thermodynamics, because you can consider a matter with large entropy and then you can throw it into the black holes. But the black holes are parameterized by finite number of particles. So all these entropies actually goes into the black hole and then it is lost. So it looks like in the presence of a black hole, the entropy can in fact decrease. But second law of thermodynamics, he said that it cannot be violated. So therefore, black holes must be associated with some entropy also, so that you throw some matter into the black hole, then the entropy of the surrounding decreases, but the entropy of the black hole increases, and in the whole process, the net entropy, the total entropy of the black hole, and then the matter outside the black hole, this increases. So delta S total is greater than or equal to 0. So he proposed this to be the generalized second law by saying that some entropy must be associated with the black hole. But what can this entropy be? Bekenstein proposed that this entropy must actually be proportional to the area of the black hole. Why area, why not volume, and so on and so forth. The reason is that area is actually, you consider the mass of a black hole. For Schwarzschild black hole, it's fine, it can always increase. But if you consider a rotating black hole, the mass can in fact decrease by a process what is called as the Penrose process. Okay, so the mass is not a monotonically increasing function, but there are some theorems. Hawking came up with something which is called as the irreducible mass of a black hole. It is related to the area of the black hole, and then Hawking has proved that this quantity is not decreasing; it's monotonically increasing. So Bekenstein proposed, because area is a non-decreasing function associated with a black hole, so the entropy must be proportional to the area, and then the dimensional counting says that these parameters should actually be there, and then Hawking did a systematic calculation, and then he indeed derived this entropy here, okay, with all these coefficients here. That's why this is known as the Bekenstein-Hawking entropy. And then this entropy, this black hole, because it's a thermodynamic object, it should also have a temperature, and the temperature of the black hole is given by this kappa divided by 2 pi. This kappa is what I had introduced a little while ago. You can see this is what is kappa, it's 1/4m. Okay? So this is a very funny system. I just want to mention it here, because there is a 1/m here, So a black hole, a Schwarzschild black hole in principle can radiate, so its mass is going to decrease, okay? But if mass is going to decrease, its temperature is going to increase, okay? So it will radiate even more, so it will decay fast, okay? So that's how these quantities will decrease, they will radiate. This is a system with negative specific heat, and I will very quickly go over this. You see, if black holes are, in physics, what statistical mechanics says that entropy is associated with the degeneracy, okay? So there is a microscopic description for the entropy of a thermodynamic system, and then that comes because of the degeneracy of states associated with that particular system. Then one can ask, what is the analogous result for black holes? And then it so happens that in string theory there are black hole solutions which obey some particular relations. They are called as supersymmetric black holes. One can actually compute the degeneracy of states, and then from there one can compute the entropy. And then it so happens that this counting agrees with this area formula given by Bekenstein and Hawking. And macroscopically, this is what is given by what is called as a attractor mechanism, which you have mentioned that I am working with. So that is all I wanted to say. Very quickly, I will go. Can I take some 7 minutes? Okay. So I will go through something which remember I had drawn this Penrose diagram for Schwarzschild black hole. This is with this U and V. This is what I wanted to explain. Okay, so if you want to consider R from 0 all the way to infinity, and T goes from minus infinity to infinity, then this is the region that you can associate it with. Okay, so U greater than mod V gives you this region here in the Penrose diagram, and V greater than mod U gives this region here. The singularity appears, there is no space-time beyond this singularity. So this is the Penrose diagram for Schwarzschild solution. But that is, nobody says you to look at R going from 0 to infinity, T goes to minus infinity to infinity. You have this metric. Where is this metric? No, it's not here. You have this metric, and then it makes perfectly sense it's without any reference to R. You can treat this to be a function of U and V, and then you can consider this metric for all values of U and V. U goes from minus infinity to plus infinity, V goes from minus infinity to plus infinity. So that will give you 2 copies of this. Okay, so that is what is this is the Kruskal extension of Schwarzschild spacetime. So RT coordinate only gives you half of this picture, but if you consider all the values of U and V, then you get this full picture. And this is the maximal extension. You can prove that you cannot go to any other coordinate and then get a bigger diagram here. This is all that you have. So this is the Kruskal extension of Schwarzschild black hole. But there is something very interesting. You can see there is this region, it's a black hole region. You can have something which can enter into, it cannot come out of this region. But there is also this region here. You can see the 45-degree lines goes here. This is the direction of increasing V. So time flows this way. So objects can come out of this region, but they cannot enter into this region. Okay. So this is what is called as the white hole. So if you consider this Kruskal extension, this also contains this white hole region. I want to focus on this particular dashed line here. Okay. So now what does it look? So this is for a particular value of V. Okay. So V equal to 0, slice is just this dotted line. Now what is this point here? This point here corresponds to R equal to Rs. But as you go this way, R increases, this way also R increases. So this is how the diagram here looks like. Okay, so it's what is called as the Einstein-Rosen bridge. That is because you see this is the spatial infinity here. There are two completely disconnected regions. If you go to r equal to infinity, the space-time becomes flat. So that is this region. Scribe plus light can go this into this region, but this region here is completely disconnected from here. It's like two copies of Minkowski space-time which are glued together here. Okay, so this is how this dotted line looks like. This is the throat here. This is the place where R becomes RS. You go this way. It's a sphere actually. The circle is a sphere. This is a sphere. The size of the sphere increases as you go far away from this throat in either direction. Okay. So it looks like there are two asymptotically flat space-times. They are connected here by this bridge, which is called as the Einstein-Rosen bridge. So you can think that you can just enter through this bridge and then you can go from one space to another space, but that's not possible because there are two regions. As you can see, nothing can go from this region. It can go from here to here only, or from here to here. Okay, nothing can go from this region to this region. The second thing is that sometime back I said that this space-time here is a static space-time, it's time independent. There is no t here, this is all static. But that's not true when you introduce this u and v coordinates. You see this is the metric here, so v is the new time here in these coordinates. Okay, and you see if you input this, r depends both on u and v. So the metric is also r depends on u and v, and it is here. So the metric is actually a time dependent metric. Okay, in these coordinate systems, the solution is no longer time independent, it's a time dependent solution. And you can see here I have embedded, this is the section that I have embedded, but this is only at a particular time. What happens, this throat starts from 0 size, it takes this maximum value r equal to rs, and then after some time again it just pinches off, it becomes 0, and then it is no longer possible to embed it. Okay, so this is how it behaves. So nothing can go from one universe to another universe. This is what is known as a wormhole, and so I will skip this part very quickly. In 1 or 2 minutes I will just go through this. So this is what these people have constructed. So this is another example of a wormhole. Okay, the wormhole that I have here, I said it is not possible to go through this wormhole because of this geometry here, because of the Penrose diagram. You cannot, because 45-degree lines go only this way, it hits r equal to 0, so nothing can go from this region to this region. But these people have constructed a metric. You can see this is completely independent of time here, okay, this metric. And this geometry again can be embedded. You can do this map, you can embed this geometry, and it actually connects two different distinct regions. So this is traversable. The metric is time independent, so you can also fall through this hole and then you can go from one region to another region. But there is one big problem here. This metric has to be a solution to Einstein's equation. And for this to be a solution to Einstein's equation, there is something which is called as the energy momentum tensor. It has to take this value here. In particular, this is the energy density. This component here gives you energy density, and this -1 says that you have to have matter with negative energy density. So there are exotic matters. No such matter is known to exist in the universe. So therefore, you cannot have a traversable wormhole. This is just a particular example, but these people have considered more general answers, and then they have showed that only in the presence of exotic matter the wormhole can be traversable. Recently, last 5-6 years, lots of work has been done. It so happens that there is one crucial thing which are called as the energy conditions, weak energy conditions, various energy conditions, which are basically conditions on this 0 component of T mu. Okay, there is something which is called as the average knowledge. It basically says that if this holds, then the wormhole is not traversable. Okay, so the average value of this T mu nu along a null direction should be positive. Okay, reasonable assumption says that this has to be positive, and that basically means that you cannot send a signal through the wormhole. But quantum mechanically, recently people have shown that you can indeed construct various solutions where this condition is violated. Classically, it's not true, but in the quantum theory, you can take various configurations, various non-local interactions, or some other constructions. Some of this which I have also worked in past, and then you can make this condition violated, that way make the wormhole to be traversable. Okay, so this is all I have to say. Thank you very much for your questions.